Our last speaker is from Brisbane. Actually, Jan Holtz is based in Peter and Naomi's group in Brisbane, is employed on one of my other grants, the John Cade Fellowship. And Jan is a bioinformatician. He came from Montpellier and was involved in the alignment of the wheat genome. So he's been on a very fast learning curve, learning about human diseases and psychiatric diseases in particular. He's got a master's degree in agronomics, and he's taken a lead role with Oligar and I looking at how to bring the comorbidity work into a data visualized framework, and very much inspired by what Andrea Garner has been doing. But I've also asked Jan to talk a little bit about the modern way that we not only democratize the data, we democratize the code. So Jan, as the last speaker, we look very much forward to your presentation. Thanks very much.
Well, thank you very much, John, for the introduction. Much appreciated. And thank you very much, Andrea, as well. It's kind of an introduction of what I'm going to say, because there is a lot of redundancy. So I'm a bioinformatician working for the Queensland Brain Institute in Brisbane. I arrived there a few months ago, and I've been involved in a few research projects involving data visualization and reproducibility. So that's what I would like to talk to you today. So two main topics, visualization and reproducibility. And my first point is to try to convince you that it can greatly improve the reader experience of your paper. And why? Because, well, if you have some good figure, then the reader is going to be able to explore your data efficiently, so he's going to understand a bit better what you've done. And if he's able to reproduce what you've done, then he's going to understand better, and maybe he's going to have more chance to use your method. And we've seen a nice graphic about that just before. And my second point is about you, the researcher, because I believe that it can really help you to take care about visualization and reproducibility. If you have some good eye-catching figure, you have more chance that people are going to read your paper. And if you have a reproducible pipeline, I strongly believe that you can be way more efficient in your data analysis. So first I'm going to speak about data viz and a few projects that I've done. And well, I like this example to try to convince people that they should visualize their data. So if we take two variables, x and y, and we know a few stuff about it, like average, variance, and we know the correlation, which is 0.8, it's very tempting to stop there and not to go further. But actually, with the same summary statistics, you can have several different ways to show what's going on. You can have some really different stories. So that's called the Enscombe Squat, and it's a very famous example in data visualization. That's another example showing pretty much the same thing, with 12 different graphics having exactly the same summary statistics. And it gets even better with that one, which is quite famous. So I believe that's definitely not a story that you want to miss in your data. So that's my main topic, like just visualize your data. So when I arrived there a few months ago, John told me, all right, we're going to work about comorbidity. And well, that was something very new for me. So I took the ICD-10 classification. So we've got 22 chapters for the whole human diseases. And these chapters are divided in groups. So we've got about 263 groups. So I was like, great, let's study the relationship between each pair of diseases. But actually, that's about 30,000 pairs of diseases. So I was trying to find a way to tell my story with a nice data viz. I end up having this circular layout, so it's exactly the same hierarchy, but like a circular one, and you've got the mental disorders in the right. The first thing I've done is I took the UK Biobank to assess the prevalence of each disease, all right? So we've got one circle for each group of disease, and the bigger the circle is, and the most frequent the disease is. So for example, you've got like hypertensive disease, which is like very, very common in the data set. And concerning mental disorders, we've got like mental disorders due to substance use with about 20,000 people concerned. And then I computed what we call the Comorbidity Index. So it's basically a comparison of the number of times you observed a pair of disease compared of what we could expect by chance. So basically, if you have a comorbidity index of 10, it means that you observe this pair of disease 10 times more than what we could expect by chance, all right? And so here you've got, for example, a link between organic disorder and degenerative disease of the nervous system. And so then I tried to understand. So I started from the highest comorbidity index. So that's all the comorbidity index over 70, right? And we've got some connection here in the poisoning group, some in the infectious group, some in the neoplasm group, and some in the mental disorders group. And this connection here is about viral infections, viral infection of the central nervous system, and inflammatory disease of the nervous system. And then I can keep going like that to tell my story, understand a bit how comorbidity works in this data set. So that's a new connection that we have here between developmental disorder and chromosomal abnormalities. And then I can keep going. And here I've got like an interesting connection between behavioral disorders and poisoning by drug. So basically it represents suicide. I can keep going, gonna skip that one. And here I start like to see some more general patterns. And one of the general patterns that we can see is that we have way more connection into each group than between groups. And that was something new for me. So for example, here for the pregnancy group, like everything is related. And for mental disorders as well, we've got like a lot of relationship between diseases. And I think we saw that during this conference. We can keep going, and we see like the more traits I have and the more like general patterns I can discover. And here it's interesting to see like that the infectious group is really related with several other groups, with many other groups. And that's the last one with comorbidity index over 10, which is still like very high. I can see that more or less everything is connected with everything. And that's one of the other messages that we have, is that comorbidity is pervasive. So why did I show this picture? Because, well, I could have done thousands and hundreds of bar charts or line charts, and could have been a bit boring. And I think using other type of visualization can greatly help to understand what's going on and to make people more focused on what you're saying. So yeah, maybe you should try other chart types sometimes. In the last few years, I've developed 2 websites called the R Graph Gallery and the Python Graph Gallery. So basically, it's a website where you have hundreds of different charts, always with the R code and the Python code, allowing to reproduce the chart. So basically, you can take your data, connect to the website, see some other type of graphics, and try them to your data. Maybe you will find something good, maybe not. But we decided to drop this project because there is a big healthy bias in the UK biobank, so it wasn't worth it to keep working on the comorbidity on this dataset, but we've got a way better dataset for that, and it's the one that Oliver presented to you yesterday. So it's the Danish register with about 5 million people. We took this dataset and we considered 10 mental disorder groups, the F chapter in the ICD-10, and we computed hazard ratio. So we've got 90 pairs, we had males and females, we've got several models, and we've got several angles of analysis. So we ended up having like many hundreds of graphics to do. So instead of putting some really long supplementary materials, we decided to build the website that Oliver has shown to you yesterday. So I'm not gonna give a huge description because he's shown more or less everything pretty well yesterday. So you remember you've got this graphic, and instead of having like several versions, you've got a button here that allows you like to check which disease interests you the most. You've got a button here to choose like which model you want to use, and you've got a button here to choose which sex you want to use. And well, I think the website is a good way to go with the paper, because it really allows the reader to explore and go directly in what it is interested in. So yeah, it was a good way to explore the data. And yeah, so just to demystify a little bit how we've done that, I think that a few years ago it would have been a very big work to do such a website. But nowadays, with the libraries that Andrea has spoken about, it gets like easier. So I guess you all know what R is, and probably ggplot2, which is just like a library allowing to do some graphics. And if you already know how to do a graphic with ggplot2, Plotly is quite magical. Basically, you've got your graphic, you just add one single line of code, and your graphic gets interactive. So you're able to zoom on it, you're able to overpoint, you're able to export it, you're able to do a lot of things with it. And then you've got this last library called Shiny that's going to allow you to transform several graphics in a website, so you can add some text and add some buttons. So yeah, as Andrea said, you cannot build some really complicated website with terabytes of data under the hood, but you can like for most of the paper you can probably present your data using that kind of technology. That's the last database project I want to show, concerns the UK Biobank. What we did is that we computed polygenic risk score for about 30 traits, and we were interested in seeing how they are clustered on a map. So for example, here it's the risk that you have to have bipolar disorder, depending on where you live. And you can see that there is a high cluster, like more people in the West than in the East. All right? And once more, like we wanted to custom this map because, well, that's 3 maps where I just changed the color scale. That's a map, but like there is a bias when you do that, is that this region, which is very big, has a more impact on what you see, all right? But there is not more people in this place, so there is no reason for that. So what you can do is to make that kind of what we call hex bin map. So instead of having big region and small region, you just take the territory and cut it in several hexagons. But when you do that, you still have a bias. It's that maybe many people are living here and just a few people are living here. So you can build what we call a cartogram, where basically all the hexagons are going to be bigger or smaller, depending on the number of people living in this area. Right, so once more, it was a lot of visualization for the same data set. And we just decided to make a website with it. Another thing we've done is to compute what we call the Moran statistics. So let's say that that's your territory. The distribution of your variable can be totally random on your territory, or it can be clustered, as we've seen, or it can be dispersed, all right? And like this Moran's value is gonna have a different value depending on what's going on. And like we run this algorithm for our 30 variables to see which one are clustered and which one are not. So that's how the website looks like. The map is interactive, so you can know exactly what's going on. You can zoom on it. You can pick up whatever trade you wanna show. You can custom your map here. And well, what I like as well is that you can load your own data. So basically, if you've got a data set with 1 line per individual and you have value for each individual, you can load it and you will have this map for your data. You will be able to compare it with all the statistics. And you will have the Moran value computed for you. So yeah, I think allowing the reutilization of what you've done for other researchers can really improve your paper. So the second part of my talk is a very, very short introduction to reproducibility because it's something that is very important to me. There is this study here. They basically took about 600 publications and tried to reproduce them. And it turned out that only 100 of them were reproducible. And well, I don't know, as a young researcher, I feel like that's not normal and that we should try to do something for it. And in the field of data analysis, I think we are all data analysts here as a researcher. I think we should take care about that. The first thing we can do is sharing our data. So that's another study where they took 200 papers published by Science. So when you publish in Science, it's mandatory to give your data with it. And they've tried to recover the data of these 200 papers. And it turned out that only 36 of them were possible to be recovered. And well, so they send emails to the authors trying to get the data, and sometimes they've got some good and, well, kind of rude answers. And I'm currently doing that for a project, and I really have some rude answers sometimes. So yeah, please share your data. And then, once your data are shared, something that you can do is try to have a reproducible pipeline. I don't know if it already happened to you to have that kind of folder in your computer. So you've got like the script 1, the script OK, the script test, script auto, script this one is the good one. Well, actually it happened to me, so I hope it happened to you as well. And then, I don't know, 1 week later, you try to redo what you've done. It takes you about an afternoon to do something that you've already done. Or maybe you have an intern working for you, doing a very good work during 6 months, and then he leaves, and you just realize that you're not able to do what he's done. So it's just like 6 months lost. So having a reproducible pipeline will avoid you to have that kind of situation. And well, there are a few best practices that you can do to avoid that. First, don't modify input files manually. So you will never have that kind of thing. Just keep an input file and do everything programming. Don't copy and paste code and result. Have a clean code, so just comment your code, because maybe somebody else is going to read your code one day. Share your code and use version control. like that you will be able to come back on your last script. You don't need to copy it. All right, and well, this resource here is a very good one if you want to learn about reproducibility, and I highly advise to have a look to it. And there is this tool that I really love if you use R. Instead of doing an R script, you can use R Markdown. Basically, it's pretty much the same. But instead of having just the code, you can put some title, some text, with some links, some images, some formatting. The code is going to do some plots, some results, some average, what you want to do. And then when you run this script, you get like a clean report with all your results and explanation in the same place. And that's pretty good, because then you just have to give this document to somebody, you click the run button, and gets exactly the same result. And in 10 years, it will still be working. And also, it allows you to put some interactive data visualization in the report, and that's quite handy. So once you've got this report, then you probably want to share it with your colleagues or in a paper or something. And there is this second tool that I would like to present today, which is Github, and which I think make a really big difference nowadays. So basically, it's a platform for developers. So each developer has a homepage. So that's my homepage. And the homepage is organized in several repositories. So I've got like one repository for one project. So now when I start a new research project, I start a new repository on GitHub, and everything I do every day, I put it on GitHub. And like that, I'm sure I don't lose anything. And the good thing is that if you share your R Markdown document on GitHub, it will automatically be turned as a website, like a small website, but still a website. And that's the way I use to share my analysis with my colleague, with John, and in my paper. Just give the URL of your GitHub repository, and everybody will have a very clean report of what you've done. And if you've got an intern, you're sure nothing is going to be lost. So that's the last tool that I wanted to present. I hope to have convinced you to plot your data and try to have a reproducible pipeline. And I really, really would like to thank John McGrath for hiring me. It's wonderful to be able to work here. Naomi Ray, Peter Fisher, and Jan Yang for hosting me in their lab, because it's really awesome to have such a scientific environment around me. And Oleg Planaripol and Abdel Abdelawi for offering me to work in their project. Thank you very much for that.
Yeah, and that's great. Actually, I discovered this guy because I was visiting his website, rgraphgallery.com, which I think has had over 1 million hits. Jan, is that right?
Oh, yeah, way more.
How many more? How many?
Well,
you're a rock star. So I visited his site. There's this fantastic site. In fact, it was one of my PhD students said, "John, you must see this great site. It's got all." So it just made our life so much easier. We were doing plots, and so you visit Jan's site, and it had it like "Who am I?" or background, and it said he was looking for a job. So it's cold email. "Hello, I'm John McGrath. Do you want to work for me?" So we got him a visa. We stole him from the Wheat Genome Institute, and so he's going back to France at the end of the year. We'll miss him dearly, but Jan, that was great talk. Questions for Jan? Discussion. I strongly recommend that you look at RM Markdown, RMD. That's been a complete revelation for me. Jerome.
That was an absolutely superb talk, and I don't say that often. I'm not. You know. So I was just very puzzled about your bipolar apologetic risk score being enriched around Cardiff.
My geography of UK is very limited.
Yeah. So.
A bit before, maybe.
The earlier one, I think. Yeah.
Bipolar, yeah.
Bipolar. So.
What's your theory, Jerome?
Because there was a UK Biobank recruitment centre in Cardiff, and Cardiff were running a big bipolar national recruitment project, and I'm just wondering if they told everyone if they were
volunteer
advertising.
Bias.
But that's absolutely. I mean, am I interpreting that right? That's like the top 14% of polygenic risk score then.
Yeah, that's it. Like you take the polygenic score, cut it in quantiles, and that's the first.
What was the Moran score for that? Was that significantly non-random?
All right, let me add something about it. So that's the Moran's value, all right? And here you see 3 values for each variable, all right? And these 3 values are with no correction, with correction with PCs, Yeah, PCs talks to, with PCs from 10,000 genomes and from PCs coming from the UKB. And you can see that when you correct this polygenic score using the PCs from the UKB, then the Morans value that shows how clusterized a variable is, it tends to be way lower. All right? And it's especially true for bipolar disorder. So the figure I've shown is that one, because I wanted to explain what we were checking. But that value is probably more accurate.
But are you fitting, when you generate your polygenic risk scores, are you fitting principal components as well?
Well, it depends. In this case, yes. In this case, no.
Right, but on that map?
On the map? Well, in this case, no. In the map you've shown just before?
Yeah.
That one? No.
No.
So that's why it looks very clustered, and it's less clustered if you take into account the correction by the UKB.
Yeah.
But I wanted to illustrate my topic, so that's why I took the most clustered one.
Okay. All right.
Any other questions for Jan? Okay, we can thank Jan for that presentation. Thank you very much.